Okay, our next speaker is Professor Thierry Bodineau from the French National Center for Scientific Research. He will be presenting a renormalizing group perspective on functional inequalities. He's also awarded the Frontiers of Science Award. Professor Bodineau's research focused on the mathematical underpinnings of statistical mechanics. He has made significant contributions to bridging the gap between mathematics and physical phenomena, such as characterizing the flow probabilities in non-equilibrium systems, understanding the physical existence and interface problems. So let's welcome Professor Thierry Bodineau.
Thank you very much. It's a great pleasure to be here. I want to report on some joint work with Roland Bauerschmidt and as well further contribution we did with Benoît Dagalier. The main point of this talk, our motivation, is trying to understand relaxation of dynamics, and which I'll explain first. And we're going to do that through renormalization group method. And I will explain how this helps to establish functional inequalities. Then, depending on time, maybe I'll say more on the application or on the related works, which have been done in parallel and in many different contexts. Just to fix ideas, one typical model of statistical mechanics we'll be interested in is Ising model, or here is a continuous version of Ising model, which is known as a 5-form model. So basically, you have, let's say, a subdomain here in Z2. On each side of the grid, lambda, there is a spin, xi. The spin takes a value in R. And you have a collection of all the spin. Let me write it large X. And this has some energy given by the following Hamiltonian. So the Hamiltonian has two parts. One is the interaction between two nearest neighbor spins. So I till j means I and ji are nearest neighbor. For example, this guy interacts with the 4 blue dots over there. And each spin is also sensitive to a potential, which typically will be like a double shape. So here, double well. So if you think of Ising model, a spin might to be at value 1 or -1, and this term says that spin tends to align with its neighbors. They want to have the same signs. So that's the kind of model you should keep in mind. And the statistics of the spin is given by a Gibbs measure, which has this form, so exponential minus hx. And we know that depending on, here is the value, I haven't mentioned T, the temperature. Depending on the temperature, this model may undergo some phase transition. When temperature is very large here, this interaction doesn't count. The system is almost independent particle. When temperature is below some critical value, phase transition may occur, and okay, we expect indeed different behavior in this model. Another related model, which I mentioned because it was part of the paper with Roland, is the Sine-Gordon model, where again you have interaction like that, like a Gaussian free field, and you add a small perturbation, gamma of cosine xi, and you may wonder whether this perturbation affects the behavior of the Gaussian free field. Now, these are two examples of model we'd like to understand, and what is the object we're interested in here is not the equilibrium, it's not the Gibbs measure, but it's a type of dynamics which is often called Langevin dynamics, or here Glauber dynamics, where you basically have a gradient descent and some noise. So, so this is over the whole spin, and meaning that each spin xi follows the gradient of its energy h, and there is at each spin some independent, for each side, some independent Brownian motion. So this is tuned such that the invariant measure is given by the Gibbs measure. It's not only invariant, it's reversible. So it makes it's a very, very nice property. And now starting away from equilibrium, we want to understand how, if I start from some initial measure mu0, I want to understand how the distribution of my particle system at time t is going to relax to the equilibrium measure. So to fix idea, it's a bit easier to say, I start from a measure mu0, and at time t, the measure is still given by a function, ft, times the invariant measure. So the evolution of this ft follows the semi-group evolution. L is a generator which is given by Laplacian minus gradient h gradient. So this, we will not really use it as such, but keep it in mind because later on this form has some relevance. But the main question, as I said, we want to address is the convergence of the distribution at time t to the invariant measure. How fast does it go to the invariant measure? So since mu t, I decided to rewrite it in terms of the invariant measure times something, the ft. One way to rephrase this is what is the convergence of ft to 1, which will be the expected limit because it's the invariant measure. So there are many ways of computing the distance between ft to 1. The simplest way is, let's say, to look at the variance, ft minus 1 to the square. And in this case, Poincaré inequality of this form. So Poincaré inequality means you take the variance of any function f, and if you can bound it by the L2 norm of the gradient times some constant, if this is known for any test function f, then you deduce the convergence of the variance of mu t towards nu with some exponentially fast behavior, and lambda being the spectral gap. Alternative way is to measure the distance in terms of entropy. So entropy now between the two measures, mu t and the invariant measure, which I'm going to write entropy of ft like that, and nth of f is f log f. So the expectation of f log f. So again, this goes to 0 when ft goes to 1, and to control the entropy, a nice functional inequality is a log Sobolev inequality. So this time, instead of the variance controlled by the Dirichlet form, namely the gradient of the L2 norm of the gradient, we control the entropy of any function, where phi is u log u. So the entropy of any function by the gradient. So if you can establish such inequality, which is the basic functional inequality we're trying to prove, if you can establish such a functional inequality, that for any function you can bound the entropy by the norm of the gradient, then you deduce a very strong convergence in entropy norm of the distribution to its invariant measure. So the goal now will be to establish this type of functional inequalities, and since we're interested in models from statistical mechanics, we of course want to address the dependence on the parameter spectral gap or log Sobolev constant with respect to the size of the domain, how many particles, to get some bounds with respect to how many particles, and of course depend on the temperature. As I said before, for the measure has different behavior, whether there is a phase transition here, there is a critical phase at Tc or uniqueness, and we don't expect at all the relaxation to be the same way depending on the values of the temperature. What is known for phi4, actually there are many more results known, in particular for Ising model, and I'll come back to that later. But in the specific case of phi-4, I just mentioned a series of works where it was so far proven that the log Sobolev constant is uniformly bounded from below, uniformly in the sense for uniformly in the number of particles, in the size of the domain, for t, let's say here large enough. So it didn't catch exactly the critical point, but for some values of t large enough, uniform bond on the log Sobolev constant were established. So one of the issues of the method I want to present is some attempt to reach this region close to the critical point, possibly, if you're lucky, the critical point, and doesn't go at all in the red region where something completely different will happen. Okay, so let's try to review. The functional inequality is a huge subject with very, very many developments, and I will not. I don't have time today to review everything. I'll review one specific theorem which was very important in terms of establishing functional inequalities, is known as the Bacri-Henry theorem. Basically, what it says is that if your energy H is strictly convex, meaning its Hn is bounded from below with gamma is positive, then immediately this ensures that you can imagine that your dynamic is going to relax fast because you have a ball which is going really fast at the bottom of the well, and there it's going to fluctuate. So what they've shown is that under this simple assumption on the Hn, the log Sobolev inequality holds, and the constant is at least given by this value gamma. So it's quantitative, and it's somehow very, very general. I mean, very general in the sense that it holds, it's not dimension dependent. Provided you have convex potential, immediately you have the result. And from that, there's a whole theory of isoperimetry, I mean, there's very, very many results which were drawn for this. One interesting result, which has been established again long time ago, is known as Caffarelli's contraction theorem. And it says that under this assumption, essentially, your measure behaves as well as a Gaussian measure. So, meaning that you can start from the Gaussian measure and transport it to the measure you're interested in with some h of x, and this map is one Lipschitz. And once you know that the map is one Lipschitz, you can deduce very many implications, and I learned that from Yair, actually. So many implications, and in particular, everything you know on terms of functional inequalities on the Gaussian, you transport immediately on the new variable. Okay, so the beauty of this result is that it's fairly general. The problem of the Bacri-Henry is that it's very rare in the application to find strictly convex potential, and in practice, the first model I've shown you is not strictly convex because the interaction is convex, but this guy is not. The second model is not strictly convex either, because even so this guy is convex, this one, as soon as z is a bit large, is not strictly convex. So, and this is basically the general type of model you'll find in the statistical mechanics. And essentially, there is a fight between two quantities. One is the interaction, which here I wrote as a kind of a Gaussian or a quadratic form. And here is a local potential. And this A will be associated with a Gaussian field which has somehow, which is convex, but very weakly convex due to the long range interaction. Instead, the local perturbation is non-convex, but it's very local. It acts on each xi. So overall, you have a competition between these local non-convexity and this more long-range, very, very weak convexity, and you'd like to understand the trade-off and how one can control the other. So ultimately, Bakri-Emery fail, the theorem, the assumption fail, but I don't know whether you can see right here. If you don't look at the measure globally, but let's focus on one spin. So here, like this spin right there in the middle, and you look at what is the field received by the spin. So what is the, in which potential this spin is going to live. It's going to live in the cosine, but it's also going to live in part of the field which is due to this x square. And if you do the math, you realize that if z is not too big, you will have the contribution of the x square of the quadratic part, which locally is quite big. So locally, if you freeze everybody, you just look at one spin, it's convex for him. The life is peaceful. The problem is trying to understand how this convexity can be transported up to the large scale and how these different type of interaction are going to match together. So that's the theme of the talk. And actually, it's not only the theme of the talk, but it's the theme of very many things which have been done in statistical physics for tons of years. And it's known as renormalization, starting from Wilson and many, many others. So what I want to explain now very briefly, but review the kind of multiscale decomposition which is done in physics, and in particular, a continuous way of decomposing, which is known as a Polchinski approach, or it's a more functional approach. Let me mention that we used heavily some old paper by Bridges and Kennedy, which was a great source of inspiration. So the question we want to address now is, can we use this renormalization method, which were devised to study equilibrium measure in order to study functional inequalities, like Log-Sobolev inequality. So let's review now the idea, and I'm going to start again from the Sine-Gordon model. So we have a lattice. Each spin is one at each side, like these dots. So xi is the value of the spin at side i. And here, in this type of model, there is a parameter z, critical point z critical, and when z here is large enough, there is a phase transition. So we don't want to go there so far. We want to look at z below the z critical, and actually, when z is equal to 0, I have a model I understand it's a Gaussian free field. So we start from this model with some value of z here, and each spin is on one side. So what we do is we're going to average out the model and make some blocks. And instead of looking at each spin xi, we're just going to look at averages over blocks of this scale. So this will give me new spin, which are indexed by the blocks. And it's first averaging, so it's at level 1. So I get a new field, and the hope is that the measure associated with x1, this new field, looks very much like this one, that's the hope, but with a parameter z1, which is a bit smaller than the z, so that the parameter has been reduced, and now I'll make bigger boxes, and I say, okay, I forget about x1, I average out all the detail at the level x1, and now I will just retain the average on my bigger boxes x2. And the hope is, again, the parameter which is associated with this next averaging is better, and Z2 is slowly approaching to 0, and 0 I know how to treat. So let me introduce some notation. When you start at scale 0, we have some Hamiltonian, H, which, okay, one of the examples we saw before. And when you do this averaging and you look at the model on the boxes, you have a new Hamiltonian, which I'm going to call H1, where some randomness has been averaged out. So, when you do it again, you have a new Hamiltonian at the level 2, which is called H2. So you have this multiscale analysis. So actually what you're interested in is trying to know what is the expectation of some function in your initial measure at the level 0. And so far, let's say after one step of renormalization, we've changed the measure, and taking the expectation of the same function under the new measure, it's not relevant. So we have averaged out things, the observable have changed, so we need to change also the function. So it doesn't matter, we will do that. So we start from a measure and some observable f of x, and this renormalization procedure gives me a new measure at the level of the boxes, and a new function, which I'm going to call f1. And for some reason, you'll see later, I will call it p1 of f. But it's a new function. And then I do it again, so I have a new measure, and I have a new observable, and everything is tuned now such that if I want to compute some expectation with respect to my initial measure with the function f, it will be the same as computing with respect to new 1 and the function p1 of f with respect to new 2 and p2 of f. So we have something, a consistent way of deforming things along the scale. So we can do slightly better, actually, for our mathematical purpose, is not to do boxes, but to do, the boxes continuously. So now you imagine that you have a way to make continuous coarse grain. We have a parameter tau, which is the level of the coarse grain, and we renormalize. So this will be, you can imagine, these are blocks of size tau, whatever it means, because tau is continuous, but these are blocks of size tau, which gives me a new measure, new tau, which is different from the new 0, and a new Hamiltonian. And this procedure allows me also to define in a continuous way how the function gets deformed by integrating along the small scale a new function p tau of f. Okay, again, I have the consistency that what I start with, I can still describe after renormalization, because I change the measure and I change the function. So far, it's very abstract, and concretely, you may wonder how you're going to deal with this object. So let's again to fix idea. Let's say we start initially from something which is a quadratic part plus some potential, which before had this form, but you could imagine something different. And at tau, at scale tau, we say, oh, it's going to generate a quadratic form, which will now, it's not called A0, but it will be called A of tau, and some new potential V of tau. So there's some arbitrariness, because I could always add some here and put it there and so on. So I have basically to decide what my A of tau will be. So I decide what the A of tau will be, and the rest is going to go in the V of tau, which a priori I don't know. But the good point is that given this quadratic decomposition, which I can choose myself, this evolution of this V of tau follows a Hamilton-Jacobi equation. So it's not like a completely arbitrary stuff. You have some equation which tells you that dt of this d tau of this renormalized potential is like Laplacian of V and gradient V squared. So it's not quite the Laplacian, and it's not quite the gradient of V, because inside this Laplacian operator and this gradient, there is the A tau is involved. It's part of the process. But overall, what you have to remind yourself is that there is a canonical way to follow the evolution of the potential through some equation. And this is what we call Polchinski equation. I didn't invent it, by the way. It's Bauerschmidt equation. So just to make sure it's clear. Now, so given this decomposition, we have the evolution of V. And what is also interesting is that the observable, which evolved according to some semigroup P tau of F, the semigroup is also described by a generator. And the generator looks very much as the Glauber generator you've seen before, in the sense that you have a Laplacian of F minus gradient of V tau gradient F. So it's, again, a bit twisted due to this decomposition in terms of A of tau, but qualitatively, it has really the same flavor as the generator of the Langevin dynamics, or the Glauber dynamics, sorry, or Glauber-Langevin. So like this one, the one we saw earlier. And for this reason, we will be able to have a like analytic treatment of the functional equation. So let me now introduce multiscale Bakry-Emery criterion. So this Bakry-Emery criterion was saying if the potential, initial potential is convex, life is easy. Here, what we're going to do is proceed slowly, and at each step, we are going to look locally at the structure of the potential. And so here, imagine that you've reached the scale tau, and you've been able to handle what's happening before. You do one small step here, and you look whether the variable associated in this small step lives into some kind of convex potential. And if they live into some kind of convex potential, then maybe locally you can apply Bakry-Emery. And then after this step, your potential should be better because you follow the renormalization group. So it should be a bit more convex. So the next step, you start again and you apply, you see whether you can apply Bakry-Emery locally. And you glue it step by step. And these are big steps, but since we have a functional setting, we can actually do it by just following these operators of the semigroup I mentioned before. So everything, this big analogy with the Glauber dynamics means like you can really run the Bakry-Emery proof, but with a different set of operators. So the outcome is the following very abstract criterion, which I'm just going to comment. So start from a measure like that with some quadratic part plus some potential. And what we claim is that so look at the blue part, and maybe if you're far away, you can look only at the blue part, which is good. If you have some control of the Hessian of the renormalized measure at point tau, if this is less than something times identity, then you can deduce a log-Sobolev inequality for the measure. So essentially, the log-Sobolev coefficient will be obtained by integrating all the small steps. So the full coefficient is obtained through the complicated integral of all these little coefficient lambda dot. So two remarks. First, there's some C dot T here which are intertwined, which actually depend on the decomposition A tau. You may forget about them originally. The other remark is that unlike, contrary to the Bakry-Emery criterion, it doesn't matter if your Hessian, the Hessian of the potential at scale tau is not perfectly convex. It can be negative. It doesn't matter because what counts is that you're going to integrate all these contributions. So if you are able to prove that the convexity gets improved or gets better, overall maybe the integral will be finite and everything will be fine. So the idea is that even so you start with a potential which is not perfect. This multiscale version of the Bakry-Emery criterion should lead to some improvement, provided, of course, you can check it. So this needs to be checked model per model. I'd like to mention that there is a recent paper by Chen and Eldad who establish a very similar criterion with a very similar method. I should come back to that. Let's just want to show one application. Again, let's go back to the case of 5.4. And for 5.4 model, one of the relevant parameters is the susceptibility, which is just the correlation between 0 and I for all the sum over all the sites in the domain. So you sum just all the correlation in the domain, and this a priori depends on the domain, but in the region, sorry, I changed T by beta because it's more canonical in this case. What can be shown is that if you have an upper bound on the susceptibility, and this result by Roland Bauerschmidt and Benoît Dagallier, then the log-Sobolev constant remains strictly positive. So you have a good control on the log-Sobolev constant uniformly on the size of your system. So this is obtained by applying the criterion and using some specific feature of this model, namely a correlation inequality by Ding, Song, and Son. Yeah? Sorry. Yes. You can cover. I mean, not only that, you can. So you can essentially. So this inequality. With that, you can relate the bound here from below, which I didn't say, to the chi beta L. So you can go up to the critical point, and you can even measure, depending on how this guy diverges at the critical point, you can measure how this guy is going to also tend to 0 in this case. So you can indeed, but it's a lower bound. It's not sharp, but it gives some understanding. Okay, maybe I mention another case where this time it's for a continuum model, so a continuum Sine-Gordon model. So there we have a system. So there the length is, if you think in terms of microscopic length, we'll say it's of order 1 over epsilon. And this would be the image of the Gaussian free field. And there the log Sobolev constant is known. It's epsilon square, and it's just given by this term. And you want to add a big delay between what I see and what I, okay. And you want to add now a perturbation, as I said earlier, like a cosine, with here a tiny, it's not very strong, it's of the order epsilon 2, and there's a term minus beta divided by 4 pi, but beta is within this range. And in this, for this model, what can be shown is that there is an infinite number of phase transition, starting from beta equal 4 pi, and then the second one is at 6 pi, and so on and so forth, all along to 8 pi. So there has been very many works to study this model. And in this case, again, you see that it's not convex because the Hessian of the Gaussian free field is of the order epsilon square, or bounded from below by epsilon square m square, and the Hessian of the perturbation is epsilon square minus something. So this is much larger than this guy. You can't apply a Bakry-Emry criterion, but in this case, you can do something. Okay, sorry. Let me mention that one of the motivations for this model is related to some SPD. So this SPD is very singular. So depending on the value of beta, when you pass 4 pi, things get quite nasty and it has to be renormalized. And this has been achieved up to 8 pi by Chandra, Eirer, and Shen in particular. So the prefactor here, I mean the good prefactor you have to put here to renormalize and to see the competition between this Laplacian and the sign is of this order. So that's why it looked a bit strange. And what we are looking is a discrete version of this dynamic. So here it's a white noise, and what we are looking is a discrete version of this dynamics. And for this discrete version, so we have been able with Roland Bauerschmidt to prove that there is indeed a Log-Sobolev inequality, which with the right order in the sense that it's 1 over epsilon square as the Gaussian free field. And we pass the first phase transition and it goes up to, this result goes up to the second phase transition. So in this case, I mentioned it because this case we obtained it not by some inequality, but by just following the Hamilton-Jacobi equation and studying the renormalized potential along the flow and proving some result. Okay. There has been related works, relatively recent, sorry, it doesn't appear yet. Okay, related work on the sign Gordon recently by Gubinelli and Meyer. And also this there is a continuum version of the 5-4 I mentioned before by Bauerschmidt and Dagalier. Okay, time runs, so I have a series of applications for Ising model, which I'm going to skip. Might talk about that later. And I want to mention a few other related results. So the first one it concerns Lipschitz maps, and it goes as follows. So when you do the renormalization, you start from some measure nu0, and as I said before, up to time tau, you erase the scale, the small scale, and remains only the large scale, and then you erase, and when you reach infinity, you erase everything, there's nothing left, so you have a Dirac mass. So one thing, and should you start from a Gaussian measure, so which is just the quadratic part, you do the same thing, you can erase a different scale, and you end up to a Dirac mass. So one thing you can do is change slightly the way you do it, such that your flow of renormalization, at least if you start from a Gaussian, it remains the same Gaussian all the time. So you just, each time you erase the scale, but you blow them slightly to keep something constant, so at least the Gaussian is constant. If you do that now, you have a new flow, the same as before, but with a slight blow up at each step. And you start from nu0, and you can show that instead of a Dirac, you end up on the Gaussian measure, G. And this gives you a way of interpolating between nu0 and the Gaussian measure. And in particular, from this, and I'll mention the result after, you can get a transport from the Gaussian measure to the initial measure. So you can really kind of integrate all this, close your eyes, and deduce a transport from the Gaussian measure to the measure nu0. So this was done by Yair Schoenfeld. So it's very much in the spirit of Caffarelli's theorem I mentioned earlier. And what Yair noticed is that if you, so as I said, there's some room in the way you decompose the measure, this A of tau, but for a specific choice of A of tau, if you can prove this multiscale criterion, then the map you built in this way is actually gamma Lipschitz. So gamma Lipschitz is gamma is just a constant obtained through this criterion. But it means that in this way, you can essentially, very much in the spirit of Caffarelli's contraction theorem, you can transport any knowledge of your Gaussian measure to your new measure, to your the probability measure you're interested in, and you transport it in such a way that you understand the Lipschitz constant, so you can recover all the functional inequalities and so on. So there's for different choices of tau in particular for the 5-4 model, we have an alternative version of this, but it's very much in the same spirit. And again, for the 5-4 model, you can transport the Gaussian limiting Gaussian measure to the 5-4 model, and you can even control how the Lipschitz coefficient blows when you approach the phase transition. Okay, so one thing I wanted to mention is now slightly in a different spirit. As you saw in the renormalization procedure, we had to adjust the measure changes, and we had to adjust the observable, which was given by p tau of f. So now imagine you have erased all the small scale and you've reached the scale tau. So now you have a measure at this large scale tau. You observe x tau, which is it's given at this large scale, and you want to recover what you've erased. What do you do? So you want to recover the small fluctuation which were in your original measure, but you kept erasing things. So to recover the fluctuation, basically you have to look at what is this semigroup doing, and this semigroup is naturally associated with stochastic dynamics, which I wrote here. So again, it depends on the decomposition and so on, so it looks ugly, but it's like a gradient V of the effective potential and some noise. So you can essentially start from this configuration and run this dynamic. So now it goes in the reverse way. Add the stochasticity up to time 0, and there the outcome of at the end of the dynamics is going to give you, sorry, it takes some time, the value of this stochastic process at time 0 will have recovered all the scale. So one way also, maybe more PD oriented, would be you have like Hamilton-Jacobi function and you look at the characteristics, and this is a way to represent the characteristics. Okay, and why do I mention that? Because this is very much related to Eldan's stochastic localization. So in order to match his work with what we've been doing, let's look again at this line. So here at time 0, there is the full measure, and we are killing the small scale up to time tau all along the way, up to time infinity, where it's a Dirac mass. So it's a bit more convenient to rescale time and to say this infinite time procedure, you do it between, let's say, time 0 and time 1. And here you are, delta 0 is your limit after time rescaling. So what Eldan introduced is a dynamics, which is actually exactly the same as the one I mentioned earlier, and it does the following job. At time here, at time 1, you start from a Dirac, and you let the dynamic run, which boils down to add slowly the small scale to the model, and at time 0, the dynamic is distributed according to the measure nu 0. So this was completely done independently, of course, of what we did. We had no idea of this correspondence, and this can be seen somehow as a counterpart of the semi-group representation, and it had this dynamical point of view had a huge consequence, in particular to prove the KLS conjecture. It also led Chen and Eldan recently to recover some functional inequalities under similar assumptions. And okay, so, and again, also I want to notice that, so a priori the stochastic localization was written in only in this term of stochastic differential equation, and Clartak and Puterman made the semi-group interpretation also recently. Okay, maybe 1 minute just to give you that all this has another counterpart, which is related to control theory. And it dates back even earlier by Fulmer. And the idea is exactly the same one. Start at time 1. Sorry, so my stochastic process are going from 1 to 0. It's a bit unusual, but you want to reproduce by starting at 0 at time 1 a measure at time 0, which will be exactly this one. So you look for a stochastic process and you look for some control function u, such that starting at 0, the function will lead you to a distribution, which is your target distribution. And you want to optimize the cost of this control, namely the square of u along the path. And this question was answered somehow by Fulmer in the 80s, and the answer says, well, but the best way of doing this is to take a u which has a gradient form and which follows the Hamilton-Jacobi equation, and there it relates the optimal cost, which is given by the gradient of the square of v is related to the entropy. So you see why it was so efficient to use that for log-Sobolev inequality. Okay, so there has been further developments related to Bouet-Dupuis formula, which I will not comment. And I just want to conclude with a brief summary. So basically, I tried to explain to you some idea of the renormalization and how through a criterion, multiscale by Craymery criterion can be applied. There are some applications, I've reviewed only some of them, and I guess there are also a set of interesting work which have been done by different people, completely unaware of what the other were doing, and we now realize that all these things are connecting, and it's actually very nice. Thank you very much for your attention.
Okay, thanks for the nice talk. Any questions from our audience?
Yeah, so I have two questions. Maybe the first question is for San-Gordon model, we mentioned now the condition is beta smaller than 6 pi. So do we expect this result can go beyond this point?
Yeah. I expect that it's feasible. The problem is that at each phase transition, and you have an infinity, you have to renormalize your potential. And there are terms which are blowing, and in this, the way we do it, we have to remove them by hand or to control their averaging, and it's not easy. So 6 pi was a technical limitation for us, but you're welcome to do the next terms.
So the second question is a little related, because now we try to prove log-Sobolev inequality, and we know log-Sobolev inequality is usually stronger than Pontchartrain inequality. Log-Sobolev inequality is stronger than Pontchartrain inequality.
Yes.
So for example, if we relax us to focus on Pontchartrain inequality, maybe we can go beyond 6 pi.
Okay, so the criterion we have is possibly too strong for Poincaré inequality, indeed, and so far we don't know how to make it better, and too strong in the sense that it's asking for some form of uniformity in terms of the Hessian. And uniformity is almost necessary for log-sub-LF because log-sub-LF gives you relaxation in very strong norm. For spectral gap, you don't need such uniformity, but you may have to change the criteria. So that's, but indeed, it could be then easier to go beyond certain threshold. Yeah, you're perfectly right. Yeah.
Thank you.
Thank you.
Any more questions? No? Okay. Let's thank Professor Thierry Bodineau again.
Thank you.